Yesterday we saw that if we had a homogeneous ODE of second order, all we needed to do to completely solve the equation, to describe all solutions to the equation, was to try and find two linearly independent solutions. Today and tomorrow we're going to talk about a technique which is called reduction of order, which is a way of taking one solution and constructing that second linearly independent solution. So if you can find just one solution to a second order differential equation, then you can use reduction of order to get the second solution to a second order differential equation. And then with those two linearly independent solutions, you can construct all possible solutions. So the technique is to guess that the second solution has the form some function times your first solution. Guess that the second function is equal to u of x times your first solution. And then try to use the ODE to determine what u of x must be. So to demonstrate the method, let's consider the following example. Someone's given us the second order differential equation y double prime minus 2y prime plus y equals 0, homogeneous second order. And let's go ahead and find the second solution to this equation if the first solution, someone has already figured out that the first solution is y1 equals e to the x. So I'm just going to make a blind stab, and let me suppose that the second solution is equal to some function times the first solution. Now if this is the case, let me go ahead and calculate what the first derivative and the second derivative would be, so that I can plug those values into the ODE and try and determine the identity of u of x. Now the first derivative has to be calculated via the product rule. So the first u of x times the derivative of the second, which is still e, plus the derivative of the first, u prime, times the second. Now to calculate y2 double prime, I'm going to have to use product rule twice, once for each of these two expressions. So here's the first times the derivative of the second, plus the second times the derivative of the first. That's product rule as applied to the first expression. And then for the second expression, we have the first times the derivative of the second, plus the second times the derivative of the first. So that's product rule as applied to the two terms in the back. Now this can be simplified ever so slightly. These two terms in the middle are a complete exact match, so they can be combined to give us 2 times u prime e to the x But that's all that can be done in terms of simplification. We could, in theory, factor an e to the x out of everything if we wanted to. I suppose that you can if you want to. So let's now go ahead and plug these expressions for the second derivative, the first derivative, and the original function into the differential equation and figure out what would need to happen in order to make the result equal to 0. So here's our y2 double prime, ux e to the x, plus 2u prime e to the x, plus u double prime e to the x. Here's our y2 first derivative, which in the ODE is multiplied by -2. ux e to the x, u prime x e to the x. And then we have our original function, which in the ODE is not multiplied by anything and it's just added in. And that needs to be equal to 0. Now let's figure out if we can combine any like terms here. For example, it looks like we have two copies of ux e to the x, but we also have a copy of minus 2 ux e to the x. So those three terms are going to cancel out. Looks like we have a copy of 2u prime e, but in the parentheses we also have a minus 2u prime e. So those are going to cancel out. So all that's left is u double prime times e to the x is equal to 0. Now e to the x we know can never equal 0. So this implies that u double prime must be equal to 0. So what does that imply about the function u? That the original function u must be equal to that constant times x plus some other constant. Maybe I'll call it capital D. So because the second derivative was found that it had to equal 0, the original function has to be linear. Now when you're doing reduction of order, the goal is simply to find any function u of x which is not constant. So for example, I could simply choose the simplest non-constant linear equation which is just u of x equals x. This would correspond to a c value of positive 1 and a d value of 0. So if u of x is equal to x, then that implies that my second solution, linearly independent from the first, is x times e to the x. Now that I have found two solutions, two linearly independent solutions to the second order differential equation, I can solve the differential equation. I can describe all possible solutions. All possible solutions must have the form a number times the original solution plus a number times the second linearly independent solution that we found. All solutions to the ODE have this form. Let's try a similar example, but slightly more robust. We have the ODE x squared y double prime plus 2x y single prime minus 6y equals 0. Someone has worked hard and they have found that one solution is given by y equals x squared. So we're going to guess that the second solution has the form some function times the first solution that we have found, with the goal being that u of x is not constant. So if that's the case, let us once again go ahead and find an expression for the first derivative. The first derivative would in this case be 2x ux plus x squared u prime. And if I apply product rule again to find the second derivative, this would we would get 2ux plus 2xu prime. That's product rule applied to the first term. And then we have 2xu prime plus x squared u double prime. And just as in the previous example, we can go ahead and combine these middle terms. Just as in the previous example, let's go ahead and let's plug these expressions into our differential equation to see what u of x would have to be in order for this differential equation to be true. So, our y double prime was multiplied by x squared, in the differential equation, so I'm going to write x squared times 2ux plus 4x y prime of x plus x squared u double prime of x. And now I'm going to go back upstairs and I'm going to say, okay, my y single prime was multiplied by 2 times x. So 2x multiplied by our expression for y single prime, which is 2x ux plus x squared u prime of x. Finally, our y2 original. Our original y in the differential equation is multiplied by -6. So -6 times our original function, and we need that to be equal to 0. So let's simplify this monstrosity and let's see what u of x needs to do in order to make that happen. Who would have expected this amount of algebra in your differential equations class, huh? So distributing through x squared, we get 2x squared times ux plus 4x cubed u prime plus x to the 4th power u double prime. Distributing the second line, we get plus 4x squared ux plus 2x cubed u prime. And distributing in the final line, we get -6x squared ux, and that needs to equal 0. Now check out what's happened with these ux terms. We have a plus 2x squared ux, a plus 4x squared ux, and a -6x squared ux. So those three terms actually cancel out. And I'll give you a hint. If you've done reduction of order correctly, that it should always happen. We also have some like terms here. We have like terms the 4x cubed u prime and the 2x cubed u prime. So in total we have x to the 4th u double prime plus 6x to the 3rd u prime equals 0. And if we cancel out the spare x's, then we get x u double prime plus 6 u prime is equal to 0. So now we basically got another differential equation. Not a differential equation in the variable y, but a differential equation in the new variable u. And so it might seem like we've kind of gone in a circle and that we have ended up in a situation that's almost as bad as what we started with. But here's the big difference between what we have now and what we started with. In our original differential equation, we had a term containing y double prime, y single prime, and the original function y. In our newly generated differential equation, we have u double prime and u single prime. But we no longer have a place where we have the original function u. So I'm going to do a change of variable. I'm going to introduce a new quantity called v, which is equal to u single prime, so that v prime will be equal to u double prime. If I make this substitution in the differential equation above, I get x times v prime plus 6 times v, which is now a first order differential equation. This is where this technique gets its name. If you do the reduction of order technique properly, then your u of x term should always cancel and you should be left with only u prime and u double prime. When you're left with u prime and u double prime, you can do a change of variable that will quite literally reduce the order of the differential equation from second order to first order. And once the differential equation is first order, we can apply any of the techniques that we learned in any of the previous sections. For example, this differential equation seems to be separable. If I rearrange some of the terms, then I get xv prime is equal to negative 6 times v, which is equivalent to 1 over v times v prime equals negative 6 over x, which in turn is equivalent to natural log absolute value of v equals negative 6 absolute value of x plus c. And if I simplify both sides, this implies that v is equal to k e to the negative 6 natural log of x, which by the usual technique can be simplified to x to the power negative 6. Now let's not forget what we're actually trying to do in this problem. Our objective is not to find v. Our objective really is not even to find u. Both v and u were tools that we introduced as we were trying to find the second solution, y. So finding v is just one step along the road. To find u, let's go ahead and reintroduce u prime where v was. Now to find the actual value of u, we can integrate this quantity. And once again, we're really only looking for a single non-constant u. So let's go ahead and pick the simplest function of this form. Maybe u of x equals just x to the minus 5. Now that we've chosen the simplest version of u of x, we can get our function y sub 2. Y sub 2 is equal to this simple choice of u of x multiplied by our original given function. So the second function, independent from the first, is just x to the negative 3. Now that we've obtained two linearly independent solutions, we can describe the general solution to the ODE, some number times the first solution, x squared, and then some number times the second solution, x to the minus 3. Any solution to the differential equation must have this form. That concludes today's material. Today we talked about a technique that can be used to take one solution to a second order homogeneous ODE and manufacture a second linearly independent solution. The technique is to guess that the second solution has the form function of x times your first solution. With that guess, use product rule to find the values of y prime and y double prime and plug them into your differential equation. If you're very, very lucky, as we were in the first example, in your differential equation, both u and u single prime will completely vanish. But at a minimum, if you've done your work correctly, once you plug in the y prime, and y double prime, the term containing just u should always vanish, which will leave you with a differential equation that you can reduce the order by changing the variable from u to v and set u prime equal to v.